Hi, everyone. I am Alessandro Sangiorgi, and I'm a software engineer at Red Hat in Emerging Technologies Office of the CTO. And this is my teammate, Maryam Tahhan, which is a principal software engineer in my team. So today, we're going to talk about from cold start to warp speed, Triton kernel caching with OCI container images. So this is just a quick agenda of what we will talk about today. And so I want to start with definition. What is Triton? So in this case, in this talk, we don't talk about Triton inference server, which is an NVIDIA product, but we talk about the OpenAI open source, no open governance, language, and the compiler for writing high-performance GPU kernels in Python. So instead of writing our GPU kernels in, for example, in CUDA, which is like much harder than Python, right? So we can write efficient GPU kernel using the Triton DSL. So how it works? So we write our Triton kernel using the Triton DSL, and then there is the Triton compiler that will compile device-specific binaries. So upstream right now, Triton supports NVIDIA and AMD GPUs. So the artifact of those are the Cubin and HSeco. And then the GPU kernels will be launched in the GPU, right? So today we're going to talk about a main problem that we have in Triton. So the first run is slow. So since Triton compiles at runtime, so the JIT, which is the just-in-time, compiles kernels, and the auto-tuner tries multiple configs before service, which means we have a long time to first token. So now let's think about a distributed environment, for example, a Kubernetes environment. We're going to have our replicas, K-kernels, C-configs, and which means we're going to have repeated compiles, CPU, GPU spikes, and delayed pod ready. So and now let's focus on bare metal. So local only, the cache is very opaque. So I'm going to show you something later, but we're going to have hundreds, if not thousands, of directories with no index provenance, not portable across nodes, containers, no signing. So the solution is to pre-build GPU kernels, package, and sign as OCI images, reuse at deploy time. So we worked on these two solutions, which are like MCU, model cache utils, and GKM, a GPU kernel manager. So managed by these two solutions for search, pruning, tracking, and Kubernetes integration. So Maryam will show later that from our demo, we have 2 times faster startup in a Kubernetes environment, which is very good. So model cache utils is a suite of tools for model kernel cache lifecycle management, and it consists of 2 main tools, the model cache manager and the model cache vault. So Model Cache Manager, MCM. So as I said before, we have 2 main issues on the Triton cache. So we're going to have cache sprawl, so redundant old kernels, bloat disks, and also blind spot, so limited visibility into GPU kernel cache and access patterns. So the goal of MCM is to make caches observable, portable, and manageable. So to doing so, MCM has a different feature, so index and search, so scan cache directories and store kernel metadata in a database, and query kernels by name, architecture, cache hits, etc. Prune to remove unused or old kernels to reclaim disk space. And then we also have a warm service to pre-generate VLLM caches in containers for faster startup. Because VLLM with a new backend, with a V1 backend, underneath it uses tosh.compile, which uses Triton. And then also track, so record runtime cache hits and last access times. So now I have to switch laptop for the quick live demo. Let's see if it works. Okay, let's see. Let's just unify. Let's see if it works. Okay, so just to give you an overview on how the Triton cache is presented to the users. This is a common, Triton cache folder. So you see, you have a bunch of. Actually, we have in this case 228 folders in which we have GPU kernel stored. For example, this is just an example. So in this case, we have, as you can see from the file name, an attention kernel, and we have, as I said before, like QBin because I'm working in an NVIDIA environment, and also the intermediate representations, etc. One important file is the metadata, in which there are like multiple information about this kernel. So as you can see here, we don't have a lot of visibility on the kernel cache, right? So for this reason, we created MCM, which is a model cache manager. So MCM consists of multiple tools, as I said before. So the first thing we gotta do is the index, right? We need to index all this kernel. So we just index this kernel, and we see here that we have 188 GPU kernels in that folder. And so we can easily, see those kernel in a human-readable way, like in a table, like in this example here. And we can also filter by, for example, by name. In this example, I'm just, filtering by the add kernel. And you can go to the helper of the list, and you can see that we have many filter options. Okay. So it's flickering. I'm sorry. Okay. So another functionality of MCM is the pruning. So we can prune in multiple ways. So we can prune using multiple filters, for example, by name, backhand, architecture, also cache hits, numbers, etc. So, for example, if we want to prune, let's say, the soft kernel that we already have in our cache, it's very easy. We just put the name there, and we just delete it. So another functionality of MCM is the worm service. I'm not going to run it now because it's a longish process. But what the worm service does, so it runs a Podman container in which there is a VLLM instance for the offline inference, with which creates the generated GPU kernels. And then we bind a volume in order to have the cache in the host, and then we can reuse the cache in a very easy way. So, and in addition to that, what the worm service does, it also store a metadata with which we can ensure that we can reuse the cache, right? We have also, for example, here, the hardware that we used, and also the CUDA version, etc. So last but not least, we have also our tracker, which is a custom Triton cache manager. It's very easy to use. We just need to export our environment variable, Triton cache manager, and point out to our, and then it's very easy. So as I said before, so what we do here with this tracker, we just track whenever the cache was hit. So we saw before that the add kernel had 0 hits, and the last access was yesterday, right? So if we try to run, for example, the same kernel, which was the vector add, we are going to see that now we have one cache hit and also a new last access time. So now I'm going to pass the ball to Maryam, and we have to switch again the laptop. Sorry for this.
Thanks, Alessandro. Seems like we didn't make a big enough sacrifice to the demo gods earlier this morning, but we'll try our best to keep going. So I'm going to talk a little bit about Model Cache Vault, or MCV. And MCV is the utility that we use to essentially package Triton or VLLM caches into OCI container images for easy distribution. So what you do is you essentially point MCV at either your Triton cache directory or your VLLM cache directory, and you ask it to create an OCI container image. It will package up that cache in one of those images, essentially using either Builda or Docker, and then that image is ready to be pushed up to Docker Hub or Quay. And you can sign those images then cryptographically using something like cosign, which means that essentially when you go to use one of these kernels, you can now trust that that's the kernel that you indeed produced and signed in the first place. So in terms of the consumption path, what you would do is you would essentially use cosign to verify the signature of the OCI container image, to verify that it is a trusted kernel that you want to use. And then you would issue an extract command to MCV to extract that cache. It will not only extract the cache, but it will also compare the cache to the hardware to make sure that essentially they are compatible. So it performs what we call pre-flight checks. If the cache is not compatible, it will warn and won't extract. However, if you do wish to extract, you can still extract it. But I would warn not to do that, because essentially you won't be able to take advantage of bypassing the JIT compilation. So what's really nice about sharing caches in this way is that this is the pretty standard way that we're now sharing models or parts of models, if people are familiar with either the Model Pack project or modctl. So this just becomes another artifact that contains something else that belongs to a model. It fits into the Kubernetes context pretty well because it's just another container image. And it can work with CI/CD pipelines. We actually have some set up for our project in GitHub to pre-generate or automatically generate OCI container images for some cache examples that we have. And that pretty much concludes the MCU portion of the talk right now. So these will form essentially the bare metal solution for managing your Triton or VLLM caches and distributing them using OCI container images. And these kind of utilities form the building block of the next thing that we're going to talk about, which is GKM, or GPU Kernel Manager. So GPU Kernel Manager is a Kubernetes operator whose role it is to pre-extract these compiled caches onto the worker nodes into your cluster so that they're made available then for pods to consume and accelerate their startup time. Like any Kubernetes operator, it consists of a bunch of CRDs, or custom resource definitions. It has a controller, and it has a daemon set that runs on each node, which is a node agent. And it also has its own CSI or container storage interface driver. So let's talk about what you would do if you wanted to distribute one of these caches throughout your Kubernetes cluster. So the first thing you would do is essentially create a cache CRD, as we can see in the example here. We're creating one for the flash attention ROCm kernel. And what's really important is, I guess, the kind. It's just a GKM cache kind. We have different types of caches that we support, but that's just one of them. The image is just a Quay image that we can see here. So as soon as one of these cache CRDs is created, the GKM controller kicks in. The first thing that it's going to do is it's going to verify the image signature to make sure that this is indeed a cache that we trust to use in our cluster. And the next thing that it's going to do is it's essentially going to resolve the image, the tag specifically, into a digest. Essentially, we use this digest rather than image tag throughout the rest of the cluster to make sure that we are using, indeed, the trusted image that the controller verified in the first place. Now, on each worker node, we have this node agent, and he, or it, I should say, is also watching each of these cache CRDs as they're getting created. It essentially watches for this update with the resolved digest in the form of an annotation. And once it sees this resolved digest on a cache CRD, it essentially knows that it's time to go ahead and expand that cache on the node. So it pulls the OCI container image, it performs those pre-flight checks to make sure we're compatible with the hardware on the node, and if we are, it extracts that cache from the container image to somewhere on the node. And just like that, we now have a cache ready to be consumed by a VLLM pod, for example, if it comes up on our system. So let's talk about what you need to define if you want to consume this cache. So as we can see in the pod specification here, we have a specific volume that we're defining at the bottom of that specification right now. And the really important part is that we are using a CSI GKM.io driver, which we specify here. And in the volume attributes, we're also specifying which GKM cache exactly we want to use. In this case, it's the flash attention ROCm cache, which is what we defined in the CRD earlier on. When you go to deploy one of these pods, Kubelet will essentially kick our GKM CSI driver, whose role it is essentially to find where that cache was extracted on the node and make it available by mounting it as a volume into the pod. And voila, just like that, you accelerate model startup time. And so what I'm going to show you is essentially a demo of this right now. So actually, sorry, it's going to be recorded because, like I said, demo gods have not smiled upon us today. But what we're going to do is we're actually going to have a single node Kubernetes cluster. We're going to have GKM installed in that cluster, and we're going to bring up two VLLM pods side by side. One pod is going to have this cached volume definition that we see on the slide, and the other one is just going to be a vanilla VLLM pod without any pre-caching. We're going to monitor how long it takes to start up those two pods side by side. Sorry. Don't think so. This is what happens when you have to switch laptops mid. Okay, so the first thing I'm going to show you is that we actually do have cache expanded on the cluster. So as we can see here, under caches, so the model we're going to deploy is a llama model. And under caches, we have a llama 318B instruct cache that's been extracted already on the node. No, because it's a video. So we're going to just have a look at the pod spec for the two pods. So on your right-hand side, you're going to see the pod that's going to have the GKM cache. We can see here we have this volume mount model cache volume, and it's mounting our cache to the home, the VLLM directory for where caches are stored. And we're going to see further down is our CSI GKM.io driver using the same llama cache that's been expanded on the node. And then in the pod on your left-hand side, we're just going to see a vanilla VLLM pod with nothing special. And so we're going to start up the two pods, and we're going to follow through the logs. I'm not going to lie, the video is sped up a little bit because it does take usually a while for these to run. And this is just starting up VLLM in serving mode for both of those pods. So we can see the GKM cached model has a total startup time of 61.52 seconds there. And the vanilla pod has a total startup time of about 115 seconds. And what's really interesting is if we compare the torch compile time for, to see what the JIT penalty was in the vanilla VLLM case it takes 56.6 seconds, and in the GKM VLLM pod it takes only 11.93 seconds. So we essentially conducted this experiment a few times and used a few different models to measure both the VLLM torch compile time and the total model startup time. So you can see here, the blue bar is essentially the vanilla VLLM pod without any caching. The green bar is the GKM pre-cached pod. Obviously, lower is better, and we can see in the case of the torch compile time, there's a significant difference for each of the models. And in terms of the total startup time, we essentially halved the startup time across the board for those models as well. So that's essentially it. Thank you very much for attending our talk, and we're happy to take any questions if you have any. Yeah, go on, Eric. Mike?
I was wondering, you mentioned you used a daemon set deployment. Is that, like, the last time I tried using one of those was for Spark, and it caused problems in terms of the permissions required to actually deploy it. Ginny?
Yeah, so I guess the question was, did we have any kind of permissions issues, or did we have to give the daemon set any additional permissions for it to be able to operate on the node? Realistically, the daemon set does have some permissions because it expands the cache onto a directory on the node itself. So that's the only permission you kind of have to give it. Beyond that, it shouldn't need any other permissions. But yes, typically for these kind of infrastructural daemon sets, they will require some permissions, for sure.
Is there any situation where this could be utilized in a layered way? So imagine like you have your core model that's always there, and then you swap out maybe some pre-filled context and kind of swap between those rapidly.
Yeah, that is something that we're looking at because it seems to be a pretty standard way for some of the ways, I guess, model parts are shared right now, especially in modctl under model pack. While we did consider integrating it directly in something like modctl, it didn't seem to have a natural fit or space in one of those existing projects. Ideally, we would have loved to have integrated it there. Yeah. Technically feasible.
Yeah. Any other questions? Thank you, everyone.
Thanks, everyone. And thanks for your patience.